In this video, we'll be discussing how to summarize data in tables and graphs. Now recall in the first chapter, we talked about how you could collect data. Once we have that data collected, now we need to summarize it in a way that is presentable. Tables and graphs offer a good way to be able to do that. For example, in section 2.1, we're going to organize first qualitative data. And remember, back from the previous chapter, we discussed the differences between qualitative and quantitative data. Qualitative data is simply just categories. In other words, they cannot necessarily be ordered. In this particular example that we're going to show, we're going to do a distribution of qualitative data of M&M colors. In this table, we're going to be discussing how we can create what's called a frequency distribution table. A table that lists the frequency distribution lists all the categories of the data and then the number of occurrences of each of those individual categories. We can also do this using relative frequency. Frequency is just the total number of occurrences. Relative frequency is the proportion or percent of the observations within the category. And this is found using the formula. A relative frequency distribution lists each category of data together with the relative frequency. It is calculated by taking the frequency and dividing by the sum of all the frequencies. And you could write these as a decimal, a fraction, or a percentage. And I'm going to show you all three in this table below. So here we're going to do an example of frequency distribution table for M&M colors. I took a bag of M&Ms and I spilled out all of the contents onto this piece of paper, which I'm going to show you here. Okay, each bag of regular M&Ms has 6 different colors. This particular bag of M&Ms that I had obviously is going to be different from each other individual bag of M&Ms. So each bag of M&Ms could have a different distribution. This is just one particular sample. In this particular sample, you can count that I have 12 blue M&Ms. I can count 6 red M&Ms. I have 15 brown M&Ms, 8 orange M&Ms, 8 green, and 5 yellow. Now I'm going to take all of this information, all of these colors, and I'm going to transfer that information back onto the table that was in our lecture notes. So back to the table, you can see from my bag of M&Ms, I had 12 blue, 6 red, 15 brown, 8 orange, 8 green, and 5 yellow. And of course you can do this with your own M&Ms. And your bag could land on the exact same color distribution, but it might also differ from that. So this is what we would call a frequency distribution table. Remember, a frequency distribution table simply just lists all of the occurrences. And that's what we've done in this column right here. This is a frequency distribution table. We are done. If we want a relative frequency distribution table, we fill in the last column. This column tells me what percent of the bag each color is. And we could write those as fractions, decimals, or percentages. For example, blue has 12 of the M&Ms out of the total. Well, how many total M&Ms were there in the bag? I would have to add up this whole column. When I add up this whole column, I have a total sum of 54 M&Ms total in the bag. So there are 12 out of 54 M&Ms in the bag. That's how I would write relative frequency as a fraction. If I were to write this as a decimal, I would simply divide those two numbers, which is going to give me 0.22, which equates to 22% of the bag is blue. Now I could do this for all of the other colors. There are 6 red M&Ms, which is 11% of the bag. There are 15 brown M&Ms, which is 28% of the bag. There are 8 orange M&Ms, which is 15% of the bag. 8 green M&Ms, which is 15% of the bag. 5 yellow M&Ms, which is 9% of the bag. This is what we'll call a relative frequency distribution table. If we compare the color distribution from each sample to each sample, for example, if you were to have done this from home or compared with other people possibly in the classroom with all a different bag, what can we say about the distributions? Well, the sample distributions, they might be equal, but it's unlikely. It's more likely that they will be different. So sample distributions can be equal. In other words, your bag might be the same as my bag. However, it is unlikely. It's more probable that your bag came out to some sort of different distribution. Maybe 4 colors were the same, but maybe green and yellow was different. In fact, you might not even have had 54 M&Ms in your bag. You might have had 53. A table is one way to graph qualitative data. Another way to do it is in a picture view, which is called a bar graph. A bar graph is constructed by labeling each category of data on either the horizontal or vertical axis, and the frequency or the relative frequency of that category on the other axis. The height of each rectangle represents the category's frequency. So we can create a bar graph for frequency or relative frequencies here. Then let's ask some questions. First, I'm going to illustrate a bar graph. Now, a bar graph has a vertical and a horizontal axis. In a bar graph, you're going to put along the vertical axis, you're going to put the frequency. And we have the frequencies on the previous table from the previous page. Along the bottom, we will put the colors. We have blue, red, brown, orange, green, and yellow. Now these colors are going to have bars associated with them, and the height of each bar will be the frequency of each color. Our frequencies, if I go back to the previous page again, our frequencies range from 15 all the way down to 5. So I at least need to have a bar height of 15 high because brown is going to be the biggest bar. So in my chart here, I need to at least go to a height of 15. So I'm naturally just going to divide these into 5s. You could do these by 2s, by 1s, whatever you decide. So my blue color, my blue had 12 M&Ms. So I would draw a bar that is 12 in height. My red bar is going to be 6 in height since there were 6 red M&Ms in the bag. My brown, there was 15. That's going to be the biggest bar. There were 8 orange M&Ms, 8 green M&Ms, so those will be the same height, and then there were 5 yellow. So this is an example of a bar chart. So it can show you the distribution of each. It's very easy to determine by looking at a bar chart which color had the most and which color had the least. We can also do this using relative frequency. If I made the exact same graph, but this time I'm going to put relative frequency on this vertical axis instead of regular frequency, my relative frequencies, if you recall, they range from as low as 9% all the way up to 28%. So I have to make sure that my axis can handle all the way up to 28%. So I'm just going to show a maximum of 30 and divide it from there. So maybe I'll do 10 and 20. So again, I have blue, red, brown, orange, green, and yellow. So my blue rectangle is going to be 22% high. So my blue rectangle will go up to 22%. Red is going to be 11. Brown is 28. Orange is 15. Green is also 15. And then yellow is 9. So this is an example of a relative frequency bar graph. Notice again that the heights of each of the rectangles represents the frequency, or in this case, relative frequencies. So what do you notice about the shapes of both of these graphs? You're going to see that they are identical to each other. They look exactly the same. The only thing that is different is the vertical axis. The shape should be the same. This graph was created by taking these numbers and simply just dividing by 54. So they're going to have the same proportion of heights as they did over here. All we did was change the scale. Now I'm going to show you how to do the same bar chart in Statcrunch. Statcrunch is a product that you have gotten when you purchased your My Math Lab or My Stat Lab account. Statcrunch is a informational center where you can put data and you can create pictures from that data. For example, in the notes, it tells us to go ahead and put our information with the colors under the variable 1. So our colors were blue, red, brown, orange, green, and yellow. Then it goes and tells us to put the frequencies in variable 2. So we had 12 blue, 6 red, 15 brown, 8 orange, 8 green, and 5 yellow. Once we've put the data into Statcrunch, then we can go ahead and we can even change the titles of the variables. If we just click on this, we can change the title of this to colors. And this would be frequency. After we've done that, according to the instructions in the lecture notes, we're going to now go to the Graph button, click on Bar Plot, and with Summary. This is simply just a summary of all of our data. Okay? If we were to click on With Data, it would have blue, 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 brown, 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 red, 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 brown, red, yellow, yellow, green. And you have a list of 54 colors. We have a summary. We've already counted all of them. So we have a summary already created of each of the colors. So our bar plot is going to be with the summary instead of all of the whole list of 54 different M&Ms. In the next one, we're going to select the categories. The categories of the qualitative data are the colors, which were located in the variable 1. We've already renamed it as colors. The counts, or the frequencies, are in the frequency column, which was variable 2. If we go to order by, let's go to worksheet, which means they're going to order these by the order that they are listed within the worksheet. So that way it looks identical to what we have in our notes. You could change colors. You could even put axis labels on here. So like the axis label maybe we'll make it colors, for example, and the y-axis will be frequency. You could even put a title on your graph. We can call this plain M&M distribution. Let's go ahead and compute and let's see what this picture looks like. So this picture should look very similar to what we did in the lecture notes already. The distribution is the heights of each of these bars because the colors should be in the same order in which I distributed them. Other options within here, if we just click edit on our options, we could change the type to relative frequency or percent of relative frequency. If we change to percent, watch what happens to the left-hand column. Instead of being frequency, these should now be relative frequencies or percentages. Notice that the brown goes all the way up to 28%. So these are now in percentages, not total counts. You could show those if you want as a decimal. If I do it as relative frequency, it will show those then as decimals instead, if you don't want the percentages. Other options we have within there is we can change the order. So the type, if we go by order by, we can do value ascending. So in other words, the value of the colors, now it looks like they're in alphabetical order. So it's ascending by alphabetical order. We can change how we group these together. We could do descending if we want, and also count ascending. So if we go by count ascending, notice that it puts brown last and yellow first, so they are in order. Let's put brown first this time. Let's go back to edit and let's go to count. Let's do count ascending by frequency. I wanted those to flop around. Let's do descending. There we go. So now it put brown first, and then it decreases from there. Which leads me into the next topic on your lecture notes. Back to our lecture notes, we're going to discuss what is a Pareto chart. It's the same thing as a bar graph, but the bars are drawn in descending order of frequency. So we'll start with the biggest bar, which is the brown bar. It will decrease from the biggest all the way down to the smallest, which would be the yellow bar. So let's create a Pareto chart here. We've already done it in Statcrunch, but let's go ahead and do it by hand. So by hand, we'll still have the colors. This time it'll be brown because brown will be the biggest. So remember, our frequencies go all the way up to 15. So the brown has 15 brown M&Ms. The next biggest would be blue, and blue had 12. The next biggest would be green and orange, both have 8. The next biggest would be red with 6 and yellow with 5. So a Pareto chart is the same as the bar chart. They're just written in descending order. And sometimes this is nice so that the largest bar is first, which some could claim as the most important bar since it has the most frequented color or distribution. The third type of graph we're going to discuss is the pie chart. And everybody knows what a pie chart is. It's also called a circle graph. but it's a circle divided into sectors or pieces of the pie. Each sector represents a category of data. The area of each sector is proportional to the frequency of the category. For example, if this is my bag of M&Ms, we know that brown makes up 28% of the bag. So we would show a piece of the pie that is 28% brown. We know blue takes up 22% of the bag. Green and yellow are both 15% of the bag. And finally, red is 11. And orange is 9. So this would be an example of a pie chart. Sometimes a little difficult to do by hand. If you're trying to make this exact, you would need a protractor and figure out what 28% of 360 degrees is to find out exactly what that angle measurement is. It's much easier to do this in Statcrunch. In Statcrunch, we're going to go to the Graph tab, Pie Chart, and this time again we'll do a summary using the same data that we had before. Again, we're going to put our categories, which is the colors column, and the counts are in the frequency column. Now I'm not going to change anything else in here. I'm just going to go ahead and compute. And you'll see that we have a bar chart, or excuse me, a pie graph based on all the information we had before. You can change how this data is displayed by going to your edit key. You can create titles. You can change the color scheme. So if we want to do a grayscale, we can. You could even change the specific colors of each. We could even go to display just the counts instead of the percentages, or you can display just the percent instead of the accounts. And so when I do that, it's now in grayscale, and then it gives the percentages off here to the side. Now we're going to resume our discussion in the next section, which deals with how to organize. Now we're going to move on to quantitative data. This is going to be what the bulk of our class is going to be about, which is numerical data. Remember, numerical data can be described as either being discrete or continuous. Discrete data is countable data, usually whole numbers, but it's not exclusive to just whole numbers. Where continuous data means you can have partial fractions and decimals between those integers. This is an example of discrete quantitative data. Let's say the fast food restaurant Wendy's. They want to know the typical number of customers who arrive during lunch hour. So a frequency distribution for 40 randomly selected 15-minute intervals during lunch is shown below. So I had a number of customers and how many times each of those randomly selected 15-minute intervals occurred. So I selected a 15-minute interval, and in one particular 15-minute interval, I only had one customer one time. In another 15-minute interval, let's say this is 12:15 to 12:30, there were 6 times that 2 customers showed up in that 15-minute interval, and so on. So if I counted all of these tallies, or in other words, all of these frequencies, you're going to see that there were a number of people that came to the Wendy's in this particular time. If we counted all of these up, you would see that we would have 40. Okay? 40 different intervals. The relative frequency is found by dividing how many times that one customer occurred, which was one time, out of those 40 different intervals. So you'll see that the relative frequency is here as well. Relative frequencies will always total a decimal of 1 or 100%. Of course, that's using rounding, and if you did round, sometimes that occurs to 99% or maybe 101%, depending on how these numbers were rounded. Now, from this particular distribution, we can now create a dot plot. A dot plot is created by placing each observation horizontally in increasing order and placing a dot each time it observed. This provides a quick picture of the data. Let's show a picture here. So we have a horizontal scale, and we're going to place each observation horizontally in increasing order. So in other words, you could have one customer, two customers, 3, 4, 5, 6, 7, 8, 9, and 10 customers total. Actually, we could go all the way up to 11. So there is no vertical axis, but we are just going to place a dot atop each observation that occurs. So the number of times one customer came during a 15-minute interval was one time. How many times did two customers show up? 6 times, 6 different intervals. 2 customers showed up. There was only one instance where there were 3 customers. There was 4 instances where 4 customers showed up. 7 instances where 5 customers showed up, and so on. I'm going to pause here and let you complete the graph. This is how the dot plot would look after you fully completed it. Notice that the distribution has the tallest dot column in the 6 customer mark. It's very similar to a bar graph, except for they're written with dots instead of bars around the dots. But they can be looked at and viewed as having the similar type of a feel as a bar graph. This can also be done in Statcrunch. The difference in Statcrunch, though, however, is the data has to be raw. It cannot be summarized. So you'll see that I have the data written in the left-hand column here. There was one time there was one customer. There were 6 times that there were 2 customers. One time there was 3 customers, and so on. So I wrote all of the raw data, and if I scroll down, you can see that it goes all the way to 40 different customers, number of frequency intervals. Now what I'm going to do with all of that raw data is I'm going to go up to Graph, and there's a dot plot option. So at the very top, I select the column where my data is. That's all I have to do. If I hit Compute, I should get a dot plot that looks very similar to the one in your lecture notes. Now in this next example on the next page, we're going to be talking still about quantitative data, but now we're going to be moving over to continuous data. Remember, continuous data means it's not countable. So suppose I'm considering investing in a Roth IRA, and I'm going to collect the data which represents the 5-year return of a simple random sample of 40 large blended mutual funds. And these are the rate of returns. So in one particular 5-year rate of return, I got a 3.27% back on my investment. Now, of course, this investment has a large amount of decimals after that. These are just rounded. So this is an example of continuous data, because I could have 3.27, 3.265538. I could have many different intervals of data in between the countable values of integers 3 and 4. Those would be discrete. So this is continuous data. And there's 40 different rates of return. You could even see in one particular instance, I got as high as a 12% back on my return. And other times I got a low amount as low as 3% back. Using continuous data, what we usually like to describe that data in as far as a picture form is called a histogram. A histogram is constructed by drawing rectangles for each class of data, which is very similar to a bar graph. The width of each rectangle is the same, but in this case the rectangles must touch each other. So that's the main difference between a histogram and a bar graph, is that in a histogram the rectangles touch each other. The classes are the categories into which the data is grouped. When a data set consists of a large number of discrete values, or if the data set consists of continuous data, we have to create these classes using intervals of numbers. So each one of these specific values isn't going to have its own bar. We're going to create an interval or a class. We might say, how many numbers in here are between 3 and 4? Well, obviously all of these values are between 3 and 4, and we would find any others that belong to that class. So we're finding how many belong in a certain interval, since each particular value is indeed different from each other. Notice that there is no correct way to create classes to summarize the data, but there are some things you should keep in mind. First, choose the smallest observation in the data, or a convenient number that is slightly smaller, and this will be the lower class limit for the first class. So if we go back up to my data and I look for the smallest possible value, the smallest possible value seems to be 3.22. So this would be the smallest value. So that's going to be our starting point for the lower class. So if 3.22 is going to be the smallest possible number, you might want to use something that's more convenient or a little bit smaller than that. So a whole number of 3 might be the smallest value I might use in my class interval. So this is going to be my lower limit. Then I want to choose somewhere between 5 and 20 classes. So I only want 5 bars or all the way up to 20 bars. But I don't want less than 5, otherwise you don't really have a good distribution. If you have so few of bars, you can't really tell what the distribution is going to be. And anything over 20 just looks cumbersome. So you really want somewhere between 5 and 20 classes, or 5 or 20 bars. Once we know what the class width is going to be, we can create the width by taking the largest number and subtracting the smallest number and dividing by the number of classes and rounding up. For this example, I think it makes sense to do each individual integer as its own interval. So for example, I'm going to go from 3 all the way up to 3.99, and then the next class interval will start at 4. This would be a very good example, because when you see, when I'm done with this list, how many total classes I'll have. So let me finish this list. So I finished this list all the way from 3 all the way up to 12.99. And that left me with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes, which falls right in the interval of somewhere between 5 and 20. Notice that 3 is the lower class limit, 3.99 is the upper class limit. 4 is the lower class limit of the second class, 4.99 is the upper class limit of the second class, and so on. So now what we're going to decide is what the frequency of each of these are. So this is where you have to go back up into your data, and you have to look for how many rates of return that fell into each of these categories. And remember, your frequency should total 40. So by the time you're done with this column, all of these numbers should total 40. Once you're done figuring all of that out by using the table up above, then you're going to create the frequency, the relative frequency of each of those. So for example, if there were 10 frequencies of rates of return between 3 and 3.99, then the relative frequency would be 10 divided by 40 for the relative frequency. And remember that this column then should total 1. So I'm going to pause right here while you fill yours in, and I'll do mine, and let's see, we come back to the same information. Once you're all done filling all of those in, your values should match what I have. You'll notice that the largest category was a rate of return of somewhere between 3 to 3.99%. The next largest category was a rate of return of 4 to 4.99%. The first category, or first class, was 40% of my graph, and the next class was 32% of my graph. On the next page, we'll talk about how we can put that into what's called a histogram. So once we have this frequency distribution class and table, we're going to put that information into a histogram. So let's draw the histogram. A histogram has a vertical and a horizontal axis. The frequencies, just like the bar chart, will be over on the vertical axis, and the data, quantitative data, will be down here on the x-axis. In this case, it's going to start at 3. Notice there's a break in a scale right here. I'm going right from 0 right to 3, and then we go all the way up to 12, or excuse me, 13 actually. Because remember, the largest class is 12 to 12.99. All right, so if we bring down the information that we had above, the first class interval we have is between 3 to 3.99, so that's between 3 to 3.99, so just shy of the 4, and that needs to be as high as 16, and that's the largest bar, so I want to make sure my graph goes at least up to a height of 16. So this bar goes up to 16. It's going to be the total width of the numbers, and that's going to be the bar of in between 3 and 3.99. Now the next bar is going to start immediately afterwards at 4. Notice there is no gap in between because the number goes right from 3.99 right into 4, so there is no gap. The size of 4 to 4.99 should be a height of 13. So let me finish in my grid over here. I'll just keep having these. There we go. And then I'll just put some little tick marks in there. Okay, so this bar is going to be a height of 13, and so on. So at this point, I'd like you to pause and figure out the rest of the histogram graph. When you're all done, your histogram is going to look like mine. So you see that it has some sort of a distribution where the height is based over here between 3 to 4, 4 to 5, and then it sort of tailors off to the right-hand side. We can also do this in Statcrunch. In Statcrunch, the first thing you're going to have to do is you're going to have to write in all of the raw data. So all of this data that you can, all 40 different rates of return, these are all percentages that were given to you in the table. So I wrote all 40 values in the first variable. I could even retitle the variable column if I want to as rates of return, or ROR. The next thing we're going to do is we're going to go up to graph again. We've already done the bar plot, the pie chart, we've even done a dot plot. Now we're going to do what's called a histogram. So a histogram, what we take is the column where the information is located. So we're going to select ROR, and then we're just going to go ahead and compute. I'm not going to change anything else. Let's compute. So this histogram should look very similar to the one that we've created in the lecture notes. Notice it has a peak over here between 3 all the way up to about 5, and then it tailors off to the right. We'll talk about distribution and shapes of distribution in upcoming sections. Notice there was another option over here for graphing. There's another graph called a stem and leaf plot. A stem and leaf plot is the next one that we're going to talk about now. So what we're going to do now is we're going to create another type of plot called a stem and leaf plot. It's another way to represent quantitative data graphically. The digits to the left of the rightmost digit form what's called the stem. Each rightmost digit forms what's called a leaf. So in order to create the stem and the leaf plot, we'll write the stems in a vertical column in increasing order, and then draw a vertical line to the right of those stems. Then we'll write the leaf in ascending order that corresponds to each of the stems on the right-hand side of the vertical line. These are best used when the data is small and the range is not too wide, so this is actually going to be a very good example of this. Let's round the mutual fund data to the nearest tenth, and let's create a stem and leaf display or plot of this data. So let me go ahead and pull that data back up, which I have here. Okay, so this was the data from the previous page, and we're going to use this data in our stem and leaf display. Okay, so in our stem and leaf display, the first thing we need is a vertical line. On the left-hand side of the vertical line, we're going to put the stem. The stem is the leftmost, the left of the rightmost digit. So it's going to be the left-hand side. In this case, it's going to be the whole number on the left-hand side of the decimal. So in this case, the vertical line is going to represent the decimal point. The whole numbers on the left-hand side of the decimal point range from 3 all the way up to 12. So my stem ranges from 3 all the way up to 12. The leaves on this side represent the numbers on the right-hand side of the decimal. And for the case of this, we're going to round each of these 2 digits to just 1 digit. So this would actually be 2.3. So I'm going to have 2.3 as one data point. So this represents 3.3. The next number is 3.3. It's the same one. So we'll write 3.3. Notice we don't write the stem again. This number is 5.4. So we'll write 5.4. 4.0. 4.2. Notice we're only writing the leaves on the right-hand side. So let's try this column again. 3.5. 10.9. 4.4. 3.2. 4.9. So I'm going to let you continue this throughout the other 30 data points. So you're going to have 40 leaves because that's 40 data points. I'll pause here. Now notice when you are all done that some of your leaves have different amounts in them as your distribution before. Remember, in your 3-point column, you had 16 values. Well, we have less than 16 because a couple of our data values rounded up to 4.0. And that's okay, but the distribution should still have the same picture format. Remember before when we did the histogram up above, the histogram had this shape where it started tall and tailored off to the right-hand side. Now if you look at this stem and leaf plot, and if we were to turn this sideways, it has the same effect. It starts tall at the 3 and the 4 mark, and then it tailors off to the right-hand side. So it still has the same distribution as the histogram, it's just written in a horizontal fashion instead of a vertical one. Now, one last thing, stem and leaf displays also normally have the leaves written in ascending order. So really, we should rewrite this in ascending order. We should start as low as 2, and we should write this as 2, 2, 3, 3, 3, all the way up to whatever the largest number is. And we should write these in ascending order. Something similar more to what I have in your answer key, which looks more like this. Notice I rewrote my stem or my leaves in ascending order, started from the smallest leaf to the biggest leaf, smallest leaf to the biggest leaf. So all I did is reorder all of the digits on the right hand side so that these were in ascending order. Now if I wanted to do this in Statcrunch, I would do the same thing as I did before. I put all of my rates of return on the left-hand side in all 40 data points. Then I would go to my graph and I would click on stem and leaf display. So instead of having the histogram over here, I'm going to do stem and leaf display instead. I'm going to select ROR as my data, and I'm not going to change anything else. I'm just going to compute. And so you'll see that this looks just like this graph over here if I were to turn this on its side. Also notice that the stem and leaf plot does in fact put these in ascending order just like we thought before. However, they did group them a little bit differently. They had 3.0 through 3.4 in one group, and then they did 3.5 through 3.9 in the next group. So they split each integer up into two separate classes. Now I'd like to discuss distribution. On the next page, you'll see that we start talking about different types of distribution. One way we can describe data is through the shape. Distributions are typically classified as symmetric, skewed left, or skewed right. Symmetric means that if we split the histogram down the middle, the right and the left side would be mirror images of each other. If the data is skewed, then the skew is named based on where the tail is. So if we looked at determining the shape of the following distributions, and let's also give an example of when we might encounter each of these. Then let's draw where the mean, median, and the mode will end up being. So this is what we're going to call uniform. This is a uniform type of a data because you can see that the frequency is the same for all possibilities. An example of this would be rolling a die. The frequency of landing each individual one of the faces of a six-sided die are going to be equally likely. So it's very probable that rolling a 1, I could land it 20 times, rolling a 2, I would land it 20 times, rolling a 3 would land it 20 times, and so on, out of a certain number of rolls. Since they're all equally likely, it's very possible that the frequency is going to be all the same. Now it says we also want to describe the mean, median, and the mode. Okay, in this case there is no mode. And the reason that there is no mode is because each of these are equally likely. The mode is always the most frequented outcome. Well, if all of them are the same, then there is no mode since they're all going to occur the same number of times. When we're talking about mean and median, I am going to draw the median in red, and I will draw the mean in blue. In this particular case, the mean and the median would be exactly halfway. So halfway of 20 would be 10. So the median, which is the middle of the graph, would be right here in the middle. The mean will also be exactly halfway, which would be the average of all this data, which is exactly halfway in between all the data. Now for the next graph down here, this is also symmetric. This is what we're going to call a symmetric graph. It's symmetric because if I were to cut this down the middle, you can see that the right-hand side and the left-hand side are mirror images of each other. An example of this would be heights. If I measured the heights of every student in the classroom, most likely it would be symmetrically distributed like this, where the mode would be the most common frequented item. In this case, the mode would be somewhere between 20 to 25 inches if this was heights. Okay, so the mode is right here in the middle because it's the tallest bar. The median, since it's symmetric, is also right here in the middle. So the median will also be in the middle, and also the mean is also in the middle. So the nice thing about symmetrical data is that the median, the mode, and the mean all occur at the same place. So they will all be equal to each other. And that's a very unique situation. So most of the things that we'll talk about throughout this book deals with symmetrical graphs. Now on the last two examples, we do have distributions that are slightly skewed, okay? This is what we call a skewed right graph. It is always going to be skewed in the direction of the tail. So for example, if this is where the peak of my graph is, the tail is skewed to the right. An example of this would be maybe ages at Ivy Tech. Right? Most students at Ivy Tech are somewhere between the ages of 18 to 25. Very, small amounts of ages, low in number. Clearly, there are some 30s and 40s, but they start to diminish as they get older. There's even some 50s, some 60s, and some 80s, but they get less and less likely to occur as we get older. This would be an example of skewed right. Now you'll see that the mode is right here at the peak, which is in the 20s. So the mode is the tallest bar. The median will be the middle. So the median will be somewhere over here, slightly skewed to the right-hand side. And because of those few outliers, that 70 and that random 80-year-old, they're really taking the average, which used to be down here near the mode and the median. And since those are such big numbers, they're really skewing the data in that direction, pulling this graph to the right. So the mean, because of these outliers, the mean is going to be in the tail. So the mode will always be the peak. Median and mean will always be in the tail in that order. So in this case, median will be smaller than mean. The opposite will be true for a skewed left graph. A skewed left graph will be an example of test scores. For example, if I were to give an exam, you would want the bulk of the exam grades to be high, maybe around 80, 90, 100. But of course, there's always a few students that get D's, like 60s or 50s. Maybe there's even a few that earned a 20 or a 10, but there are very few of them, thus skewing this data that was peaked on the large side, and those outliers are pulling the graph to the left. The mode is the tallest bar. The median is the middle of the data. And then the mean is always in the tail. And the mean will always be in the tail because of these outliers, which are drastically different than the bulk of the numbers, and they're going to pull that data into the tail. So in this case, the mean is less than the median. The last graph that we're going to talk about is a time series plot. And a time series plot needs one particular variable, which is time. And it's obtained by plotting the time in which a variable is measured on the horizontal axis and the corresponding value of the variable on the vertical axis, and then we'll connect them with lines. These are useful in identifying trends over time. So in business, sales would be a good example. For this example, we're going to show the number of housing permits that were issued between the years of 2000 to 2010 in the US, and we'll construct a time series plot. So a time series plot has two sets of axes. Always along the x-axis is going to be your independent variable, which is going to be time. So I'm going to put the years down here, starting with the year 2000 all the way up to the year 2010. Along the vertical axis, I'm going to put the number of permits. So frequency of permits. Now these are in thousands, so I'm going to write that up there, in thousands. So each of these numbers actually has 3 zeros written after it. So in the year 2000, I actually had 1,592,000 permits. In the year 2010, I actually had 592,000 permits. You can see that the number of permits obviously is drastically going down. In the year 2008, that's when the shakeup occurred, when we hit that mini recession. So we're going to plot these points in the year 2000, for example. We're going to plot a point as high as 5292. So I need to have a vertical axis that will support these numbers. The highest number is 2155. So I'm going to go as high as 25,000, or excuse me, 2500, and I'm just going to break these down into fifths. So we'll start with 500. I think I messed that scale up. 1,000, 1,500, 2,000, and then we'll do 2,500 up here. Okay? All right, so in the year 2000, I had 1,592 permits. Actually, 1,592,000. So that's right about, oops, excuse me, right about there. Okay? In the year 2001, I had 1,636. In the year 2002, I had 1,747,000 permits, and so on. So I'm going to let you draw the rest of these dots, and then I'm going to pause, and then we'll come back together. Once you've put all of your points into your graph, you'll see it has this sort of distribution. Now with a time series graph, you're always going to want to connect the points with straight lines, so not a curved line. So where each of these line segments will be independent straight lines. Not curved, straight lines in between each year. So this would be an example of a time series graph. Now for the next section, I'm going to let you read the last section. We talk about how often statistics get a bad reputation for having the ability to manipulate data to support a specific position. One method of distorting the truth is through graphics. Graphs can be misleading if they unintentionally create an incorrect impression. Graphs can be also deceptive if they purposefully create an incorrect impression. The most common graphical misrepresentations of data involve the scale of the graph, an inconsistent scale, or a misplaced origin. The first link on that page links you to the Wikipedia misleading graph, and this is the first one that comes up. You can see that a regular pie chart over here to the side shows the accurate proportions of each sector. The green is only 5% and represented as 5% of the angle, which is the appropriate amount. But if you show it as a three-dimensional version and you look at that piece of the pie and you specifically put it in front, so the perspective of anything in the front is going to be larger than anything in the back, it makes it look like that green piece of the pie is actually bigger than the blue. But when you lay it out flat from a bird's eye perspective, it's clearly not the case. In fact, it's less than half the size. So sometimes showing things in three-dimensional and putting things in the front will draw the attention more to those specific items. This is one idea of how we can create bias from using pictures and tables, and we want to be careful about doing things like that. In the lecture notes, there are many other links that I'd ask you to click on from home and look at some of those other misleading graphs and things that we should stay away from. On the last page of the lecture notes, I have an in-class activity. So I don't expect you to write this down from home because we can do this one in class. Let me show you an example of a previous class for the sake of creating a video for it. But we can replicate this in the class. So what I asked first to do is list all the heights of every student in the class. I did this for one particular semester, and first I put mine. I am 68 inches tall, and then I found the heights of everybody else in the classroom in inches. Clearly 60 inches is 5 foot, so I did have somebody that was 4'11", all the way up to 72 inches is 6 foot, 6'1", and 6'4", and I even put them in ascending order. After I had all of the heights of all of the students, the next thing it asked me to do is what type of variable is this? We learned back in Chapter 1 that the types of variables that these could be, first of all, these are numerical data, so it's going to be a quantitative type of variable. It is also continuous, because even though these look like countable values, we did round these numbers. Certainly this person is probably not 71 inches on the dot. They're probably more like 71.1 inches or something like that. So height, anything that's measured in inches or a distance, is a continuous variable. Also, it is a ratio. It is a ratio variable for two reasons. It has a true zero, in other words, 0 represents the absence of height. There is no negative values. Also, I can divide values. So for example, somebody that is exactly 72 inches is 6 foot tall. If I had another person that was 3 foot tall, then that means this person is exactly twice as tall as somebody that's 3 foot, because 6 feet divided by 3 feet is 2. When we can make those divisions like that, that means it's a ratio. We've created a ratio of the values and it means something. You can put that into a meaningful sentence. I can also create a frequency distribution table, and I'm going to create of class width 2 inches. So over here I have a class width of 2 inches. So anybody that's 58 all the way up to 60, but not including 60 inches, would fall into this class. Anybody that's 60 inches all the way up to 62, but not including 62, would fall into this class, and so on. Then I listed my frequencies of each from the data above. I had one person that was 59 inches, so they fell into the first class, one person that was 61 inches, so they fell into the second class, and so on. I am 68 inches, so I fell into this category with one other person. Then I can put all of this information into a histogram. A histogram puts all of the quantitative data down on the bottom of the x-axis. This is the amounts of inches of each person. And then I fill in a bar for the height of each person within each class, that is 2 inches wide. Again, I am 68 inches, so I'm falling somewhere in this class right here that is 2. I'm either this person or this person since there are 2 people in this bar. Now, the type of symmetry that this bar has isn't exactly one that we've talked about before. It's definitely not skewed. It doesn't look like it has a tail. It almost looks like it's symmetrical, except for there's a gap in the middle. It comes to a peak, drops, and comes to another peak and drops again. So it's almost as if there's 2 separate peaks. We call that bimodal. In other words, there's actually 2 modes that are happening here and they're separate. Why do you think there happens to be 2 modes in an example of heights? Well, the reason why in heights that this potentially could end up being bimodal is because men's heights and women's heights are going to have 2 different averages. Men's heights are going to be somewhere between 70 to 72 inches on average, where women's heights are going to be somewhere between 64 to 68 on average. So my assumption is most women are down here where the men happen to be the upper part of the graph. So this is what we call bimodal. It comes to a peak, settles, and peaks again. I created now a dot plot. A dot plot I did down here, and I put all of the inches down on the bottom and a dot for each one that happens. So this is 58 inches all the way up to 78 inches, and how many occurred in each of those intervals. The dot plots don't work very well with intervals or continuous data. In other words, if there's data in between here, we generally don't use a dot plot. However, we did force one to occur. We rounded all of our data to nice whole numbers for the sake of drawing this picture. Also, a stem and leaf plot doesn't work very well enough either because we don't really get an appropriate distribution. If everybody's falling in 50 inches, 60 inches, and 70 inches, we've really only created 3 bars. So if I drew this as a histogram, then this only has 3 bars and doesn't really create much of a distribution like I have up here, which is a much better distribution in a much better picture form because it tells me what the heights of each of them are and gives me a feeling of where the outliers, the mode, the medians, and all of the mean would happen to be. So these 2 graphs would not be the best to use for this particular example. So at the bottom, when I say which is going to be the most useful, I would definitely answer this as a histogram. Let's now do all of these in Statcrunch. So the first thing I did is I put all of the heights of all of the students, including myself, into this table. Notice they don't have to be in order. In fact, I put myself first, 68, which normally I would fall somewhere down here, but they don't have to be in order. Statcrunch is smart enough to know how to put those in order itself. So the first thing we're going to do is let's look at the histogram. Remember, we went up to Graph and under Histogram. Then we're going to select the column. Oh, in this case, I'll just call it ROR. Actually, maybe I should have renamed that. Let's rename that first as heights. Okay, let's try that again. Let's go to Histogram. We're going to select the column, which is in this case is heights. And I'm not going to change anything. I'm just going to leave everything as is, and let's compute. So this histogram is going to look very similar to the one we had before. It doesn't have the bimodal because it doesn't look like the classes were split out quite as evenly as the bars were that we had on the page. We can change these class widths if you would like to by editing the graph and changing the bins. The classes are called bins in Statcrunch. So if we start the bin at, let's say, 58, and we create each width to be 1.99, or let's just call it 2, and recreate and recompute this, then the graph starts to look more like the actual graph that we have on our lecture notes, because I forced a class width to occur every 2 inches wide. This definitely does look bimodal and looks very similar to the graph on our page. If we wanted to create a dot plot, we could do so also. There's an example of the dot plot. Not super friendly or helpful because it doesn't really give me a good distribution or a good height at any particular location. We could also do a stem and leaf plot. Again, not a very good example because it doesn't give me enough information to give me a distribution. So out of these 3 graphs, I would definitely say that the histogram is the most useful.